Okay, our situation here is we have some material here. Now, the surface of the material will reflect incoming light, but it will transmit some light. The lower surface either reflects light or is attached to something else that reflects light. We adjust the properties of the material and so forth so that the amount of reflection here and the amount of light that comes from the reflected light here that's then refracted back into this medium, which is probably air, have approximately equal intensities. So the thickness of the material is T. We ask what is the path difference here? Okay, and what path difference then would result in destructive interference, because the goal of this material is to reduce glare. So it's reducing the reflections that come off of whatever this is. Typically you'd have glass down here. You have a thin coating on the glass that accomplishes the goal of reducing glare. Okay, well, first of all, let's just consider what's the path difference here. Okay, now I say the path difference, well, if the light comes in at a fairly steep angle, as indicated here, then the path difference is pretty close to 2t, or at least the distance traveled by the light is approximately 2t, t being the thickness. We got to go through the material and back. Now there's a little bit of an angle, so there's a little bit of a cosine error there, but the cosine of the angles we see here is so close to 1 that the path difference is really going to be very close to 2t, or at least the distance it travels is approximately equal to 2t. Okay, so the path difference is approximately 2t. Now, that path difference occurs in this material, and this material has an index of refraction, so that the number of wavelengths of path difference would have to be calculated in terms of the wavelength of the light within this material. So if the incoming light then has wavelength lambda, we ask what thickness will result in destructive interference. Now, the first solution I gave here, and the only one I gave in class, says, well, the path difference should be half a wavelength, and the path difference is 2t, so 2t equals half a wavelength, t equals a quarter of a wavelength. And that's valid if lambda is the wavelength of the light in the material. Now, I didn't distinguish between the wavelength of the incoming light, which is going to be different than the wavelength of the light in the material. So I'm going to use lambda prime. I'm going to modify this slightly, use lambda prime here, and lambda prime here and here. It's 1/4 lambda prime. Lambda prime is going to be the wavelength of the light in the material. So I'll just make the note here that lambda prime is going to be shorter than lambda. Okay, if the index of refraction out here is 1, then lambda prime is just going to be lambda divided by the index of refraction in the material. Okay, so index of refraction is going to be n in this material, and we assume that the index of refraction out here is 1. Okay, under these conditions, index of refraction 1 here, index of refraction n here, light slows down, which means that the wavelength is going to decrease. And it's going to decrease by factor, well, it's going to change by factor. The new wavelength will be 1/n times the original wavelength. So, so the wavelength is lambda here and here. In here, the wavelength is going to be lambda prime equals lambda over n. inside the material. If you're trying to reduce the reflection for light coming in at a greater angle, you might have to take the refracted angle here and correct for the cosine. The path difference is going to be 2t divided by the cosine of the angle here with normal. Okay, so if the cosine is 1 or close to 1, then it's just going to pretty much be 2t. If the cosine is significantly less than 1, then you're going to have to divide that 2t by the cosine. I'm not going to go through the details of that, but that's how you would handle the situation. So if you encounter a situation of that nature, you're not likely to find it on a test this year because of the shortened time we've had in this particular phase of the course. If it's not 2015, ignore that. You know, if you're looking at this in 2016 or 2017, you might well have a problem that throws those little twists in there.